a riddle that confounded the world's greatest minds for more than 3.5 centuries. Andrew Wiles' solution to Fermat's last theorem has been called the proof of the century. It is the mathematical equivalent of splitting the atom or finding the structure of DNA. It is the culmination of a struggle which involved generations of mathematicians and which has influenced every area of mathematics. Undoubtedly, the solution is a triumph of modern mathematics. The problem looks so simple that even a 10-year-old kid could understand it, yet all the great mathematicians in history couldn't solve it. Pierre de Fermat was born in 1601 in southwest France and was known as the Prince of Amateurs. This 17th century genius discovered the laws of probability and laid the foundations of calculus. But Fermat's greatest contribution was the purest and most elegant of mathematical researches, number theory, a discipline that concentrates on the properties of simple whole numbers. To the outsider, problems in number theory seem like pointless riddles with no application. But for practitioners, these conundrums are the ultimate intellectual test. Fermat invented his most famous challenge while studying an ancient Greek mathematical test, Arithmetica. One chapter described the properties of a particular equation, a squared plus b squared equals c squared. The equation is closely related to Pythagoras' theorem and simply asks for three numbers, a, b, c, such that the first number squared added to the second number squared equals the third number squared. One night, Fermat considered a slightly perverted form of the equation and wondered if it was possible to find a cube number added to another cubed, which equaled a third cube number. Eventually, he came to the conclusion that there are, in fact, no solutions to this equation. Furthermore, Fermat believed that unless the equation was squared, finding a solution would be impossible. In the margin of his Arithmetica, he wrote down that there are no solutions to the equation x to n plus y to n equals z to n, where n represents any number greater than 2. The claim that among the infinity of numbers there is none that fits the equation was shocking, but Fermat believed he could back it up with a rigorous proof. Next to the marginal note outlining the theory, the mischievous genius jotted down an additional comment that would haunt generations of mathematicians. I have a truly marvelous proof of this proposition which this margin is too narrow to contain. It was only after his death that these tantalizing marginal notes were discovered, and so began a marathon effort to rediscover Fermat's proof. Fermat made quite a habit of casually jotting down theorems without the accompanying proof. After a century, all the theorems were successfully proved, except for the one concerning the equation x to m plus y to n equals z to n, dubbed Fermat's last theorem. It became an increasingly valuable trophy for ambitious mathematicians. Prizes were offered, careers were sacrificed, and rivalries flourished. In Japan in the 50s, a breakthrough occurred. Goro Shimura and Yukata Taniyama began to examine so-called modular forms. This was the equivalent of realizing that the instructions for building life were encoded in strands of DNA. It became one of the holy grails of 20th century number theory. For 3.5 centuries, the last theorem had been a curious and impossible riddle on the edge of mathematics. Now, the most important mathematical problem from the 17th century was coupled to the most significant problem of the 20th. Then, Andrew Wiles, in his Sci-Tech study, worked on the Taniyama-Shimura conjecture for 7 years. Wiles said, what one would naively have tried to do, and what people certainly did try to do, was to count elliptic equations and count modular forms, and show that there are the same number of each, but nobody has ever found a simple way of doing that. The first problem is that there are an infinite number of each, and you can't count an infinite number. For this problem, computers would be useless, as checking an infinity of cases would take eternity. On June 23, 1993, he attended a seminar at the Sir Isaac Newton Institute in Cambridge to give a lecture describing the proof. Next month, Wiles receives the 90-year-old Wolf-Scale Prize, officially marking the end of the greatest mathematical challenge in history. Yet, there remains a question. The proof is a masterpiece of modern mathematics, which leads to the conclusion that Wiles' proof of the last theorem is not the same as Fermat's. If Fermat did not have Wiles' proof, then what did he have? I present next a simple solution to the problem that perhaps is the closest thing Fermat had in his mind. Part 1. By simply transforming x to n plus y to n equals c to n in terms of Pythagoras' theorem, we can solve Fermat's last theorem. When n equals 1, the equality holds as shown here because a right-angled triangle is formed. However, when n greater than 1, the area of the square c to n square becomes smaller than the sum of the other two squares, a to n square and b to n square, as shown here. And this is in fact the reason why the equality cannot hold when n greater than 1, as we will confirm next. When n greater than 1, the area of the square c to n square is always smaller, no matter the value of n greater than 1, than the other two squares, a to n square and b to n square, as clearly seen here. Part 2. Therefore, Beal's conjecture is also proved by the same demonstration, as changing the value of n into x, y, and z is irrelevant. The area of the square c to z square is always larger or smaller than the other two squares, no matter the value of x, y, and z in Beal's conjecture as shown here. Conclusion. Fermat's last theorem and Beal's conjecture hold true because the only time the equations hold an equality is when a right-angled triangle is formed by the two sides of the equations. I have shown you here a very simple solution to these two problems, considered by most in the field as the most difficult math problems in all of math history. One of them, Fermat's last theorem, took over 350 years to be solved by modern mathematics. The other one, Beal's conjecture, could have taken a very long time to be solved as well. But now you know the truth of the matter. By the same token, I can assure you that world poverty can be solved for good. Make everyone on earth wealthy. I also have the solution for that. And it is also very easy. Perhaps even easier than the solution of these two math problems. Would you believe me that world poverty can be solved for good by just you becoming a member right now in the social network I want to create? If you want to solve world poverty and become wealthy at the same time, become a member now and help me change the world. Subscribe to my channel and become a member now at